So today I'm going to be talking about whamm, which is a bytecode instrumentation DSL for WebAssembly. I'm Elizabeth, and yeah, I'm advised by Heather and Ben. First of all, we can agree that debugging is really difficult. Trying to isolate the problem and fix it can be kind of convoluted at times. And this gets even harder when you're debugging bytecode because it's that low-level language instead of the source code that you're getting to read through. And it can make you feel like this at times. And this is especially relevant if we think about the fact that WebAssembly is growing beyond the browser. So there are going to be a lot more people that are trying to work with WebAssembly specifically. But unfortunately, WebAssembly doesn't have a ton of tooling surrounding it, and we're wanting to change that by creating more support for people to build more instrumentation. So how are tools built? By instrumentation, what I just mentioned. So when I say instrumenting a program, what I mean is injecting some code into some point in a program's execution to do some operation, which that's a really, really hand-wavy definition intentionally because it scopes to a lot of different tools that could be written. Things like debuggers, things like collecting metrics to say, hey, these events happened X number of times during my dynamic execution. They can be really whatever you imagine for observing low-level events that occur when your programming is executing dynamically. And there are a lot of approaches to doing this. You have intrusive approaches and non-intrusive approaches, and I'm going to dig into what I mean by those. The intrusive approaches that I would categorize are things like bytecode rewriting and recompilation. And the reason why I'm saying they're intrusive is that they intrude on the application state space. So you take the application and you literally inject instructions into the application code so it's running in the same place as your application when you're executing it dynamically. And this can be dangerous if you're not careful in how you implement this instrumentation. So thinking about WebAssembly is a stack machine. You have the stack, and then you have some instrumentation executing, and then you have the stack. You want to make sure that your stack is the same before and after to make sure that you don't accidentally inject application bugs that wouldn't have been there if you hadn't injected your instrumentation. There's also non-intrusive approaches, things like emulation and direct engine support. So with these two approaches, you have a way to execute your instrumentation outside of the state space of your application. So they're running somewhere else, so they're not intruding on the application at all. And this can be a lot safer because you don't have to worry about things like the stack state. And yeah, there are trade-offs here. So you have to consider these when you're wanting to implement your instrumentation. So what makes sense to lock your instrumentation into for the tool that you're building for developers? And there are several different instrumentation frameworks for WebAssembly. I'm going to go over the 3 that I know of. If anyone knows of any more, you should let me know because that would be helpful for me. So for one, you have Wasabi, which is done via bytecode rewriting. It's done by writing your instrumentation code in JavaScript. And it's really slow because it's switching between the JavaScript and WebAssembly execution contexts when it's switching between running your application versus running your instrumentation. So this is a high-level architecture. You can see that, let me use this so that people online can see. Well, I don't know where there it is. So at the beginning, you have your program, and then you run it through Wasabi to generate your instrumented program. So this guy imports and runs functions from either the analysis, so the instrumentation that you've written. I'm also going to use the term monitor interchangeably here, or the Wasabi runtime to support what's going on. So you have your program you're wanting to observe. You have the observations that you've created and then passed to Wasabi to actually execute. So it's switching between these different contexts when it's actually running dynamically to collect whatever information you need. Then you have Walrus, which is also bytecode rewriting. This is a Rust library that you use to import your WebAssembly module. Then you can traverse the AST, do some injection of different instructions that you need to accomplish your instrumentation at runtime, and then you just run the instrumented bytecode. And this is really fast because all you're doing is injecting more instructions. Then you have Wizard, which is done via engine support. So you just interface with some API and you say, hey, I want to probe these events in my application. So it sticks these probes into my application, and then it fires callbacks to actually execute what in Wasabi was done in JavaScript. Now, this is written in Virgil, which is also a high-level language. And this is really fast because it's using the underlying engine to actually do this instrumentation of your application. So where can the built instrumentation run here? If you think about Wasabi, it can run on any Wasm engine that can also run JavaScript. With Walrus, it can run anywhere. It's literally just a Wasm module that's running, that's instrumented, so it can run anywhere the Wasm can run. And then on Wizard, you can only run on Wizard. So it's limited to the scope of applications that can run on top of that engine specifically. So obviously here, Walrus wins portability. So if you're wanting to build instrumentation that can impact a lot of developers, it would make the most sense right now to build using something that can run in most places. But unfortunately, portability isn't everything. And I'm going to dig into some reasons why it's really nice to use something like an engine that supports instrumentation directly to build your instrumentation. So here are some Wizard highlights. There's a QR code for our paper if you want to read it. So for one, as I said before, Wizard is non-intrusive instrumentation. It's also a design that's built to be feasible for production adoption. And we're hoping that more production engines will adopt this design for a lot of different reasons. So it also provides consistency guarantees, so you can have composable tooling. So let's say that there's some really wonky behavior in your application and you're trying to figure out what's going on. You could run your application, turn on a bunch of different monitors, and they can collect all this instrumentation during one run of your application. And they're not going to step on each other's toes because of the guarantees of the underlying engine that it's running on. You can also dynamically add and remove instrumentation, which is huge when you think about the fact that this design is for production adoption specifically. So if you're thinking about an application running in production, you can just dynamically turn on a monitor if you have some buggy behavior in production without reshipping binary, an instrumented binary. You can just turn on a monitor, collect information to figure out what's going on, and turn it off, and just let production continue running like normal. You can also have JIT intensification of instrumentation, which sometimes makes your instrumentation run faster than bytecode, which is bytecode rewriting, which is kind of wild, because it has instrumentation-specific JIT optimizations. So I'm going to show you here what that really means. So the full height of each of these columns is the total runtime for some instrumented program to run. And this is in the JIT. So it's a JITted instrumented program that's running. When you turn on JIT optimizations for instrumentation, it removes all of this cross-hatched space. So what's left is this just solid space in our runtime. So it removes all of this execution overhead, which is pretty huge. And you can see how impactful that can be on this chart, where it's actually showing the three different instrumentation frameworks I mentioned before. So the green column is Wasabi, which is really slow. This is a mean relative execution time at the log scale. So this is the normal runtime in application. And then Wasabi is over 10 to the third times as slow as the original application runtime, which makes sense because it's having to switch between JavaScript. Then you have the bytecode rewriting with Walrus that I mentioned over here, which this is JITted runtime. And then this is the Wizard JITted instrumentation application here. So you're running on Wizard using Wizard's instrumentation with the JIT optimizations turned off. And then this is with the optimizations turned on. So you can see how much faster it makes it, and it runs even faster than the bytecode rewriting approach. So what should we do here? What should we implement our instrumentation on? Because obviously you're going to be locking your instrumentation into one or the other. So you want to make sure that you're making the impact with your instrumentation that you want to. What we really want is the best of both worlds here, right? We want to have Wizard and Walrus. We want to have bytecode rewriting and dynamic instrumentation support with the engines. We want something like whamm, right? Something that enables us to switch context based off of the target platform we're going to be running. So whamm is a Wasm Instrumentation DSL that abstracts above the injection technique specifically. So this is an overview of whamm and the goals that we have. Some of these goals we discovered by doing a gray literature review, which is basically reading through a bunch of online content like blog posts, Stack Overflow, that type of stuff. And these first 2 points with high level and intuitive, easy to build, testable, debuggable, those were the different pain points that we saw that were pretty widespread across this gray literature review that we did. So we're going to make those some of whamm's goals. We're going to do some research to help inform how to do these things well. Yeah, because there are not many, I haven't seen any frameworks that really support testability. So you basically write your instrumentation, hook it into an application, and then see what happens. There's not really a way to unit test instrumentation right now. So I want to see if there's a way to do that through doing some research around the testability of instrumentation. Yeah, so whamm is inspired by the dtraces-d language, if y'all have used it before, to try to make it high level and intuitive. We express instrumentation in terms of predicated probes, which is the D language. So probes meaning, hey, I want to probe this event in my application as it's running. When I probe this event and when you hit it dynamically, execute this logic. And predicated meaning, if this conditional is true at runtime, then execute this logic. We want to be able to instrument events at different granularity. And I'm going to dig into some example events in a couple of different slides, or a couple slides down. And then we want to provide behavior as Wasm functions, and then we say where to call them in whamm. So if you have some pretty complex behavior, you can write it in any language that compiles to Wasm. And then in your whamm specification, you say, when this event happens, fire this Wasm function, which is going to have my instrumentation behavior in it, which is similar to the Wasabi approach, but instead of running in JavaScript, you just run in WebAssembly. We're wanting to write instrumentation once, and then whamm takes care of the injection strategy, like I've said before. So here's an example architecture of what's going on if you target any engine. So you pass your program.wasm, and then this is your whamm instrumentation definition. You pass these in along with the instrumentation library that you've compiled to Wasm, and then whamm can stitch these things together either by merging or importing this Wasm module. And the reason for this is because some use cases, you would have to merge together the two Wasm modules and have them work in the same module. And this is because of a use case that we're seeing with Definity, where you can only deploy one Wasm module at a time. So this is the way to get the instrumentation into the program without deploying multiple modules. Then you would spit out a program monitored, like an instrumented program variation, which can run on any engine. And then if you're wanting to target Wizard, you would do basically the same thing, except it would spit out that Virgil language definition of our instrumentation, which can run on Wizard, and it would be using these callbacks inside here instead. So the key takeaway, compiles either way. So this is a high-level kind of grammar of whamm, and you can use this when we're looking at an example monitor in whamm to kind of help reference back and forth. So here you're initializing your global state, correlates here, and then you're using the Wasm provider within the bytecode package, specifying this event. So when I reach this instruction, this bytecode instruction in my WebAssembly, and then using the before mode of my instrumentation. So like before this instruction executes, I want you to fire this probe logic. So this is the mode. There can be multiple different modes. There's either before, after, or alternate. Before means before this event occurs. After means after this event occurs. Alternate means instead of this event occurring, fire this logic. And then you have the predicate. So it's the conditional that needs to be true dynamically in order for any of this to execute inside the body of the probe. Set it to true for sake of simplicity, but this could be any dynamic data that you want to collect and use. Then you are executing the body of the probe because the predicate is true dynamically. Here, you're creating a new variable called index. If the top of stack is not 0, then I want index to be 1. Otherwise, I want index to be 0. And then I index into my count map with the probe function index. So like the ID of the function that this probe has been injected into, the program counter, so the offset within that probe function that I've injected my probe into. So that means the offset that this instruction exists in within my function. And then I'm using the index variable that I just created and incrementing it. So does anybody know what this is doing? What it's doing is dynamically figuring out which paths within this BR instruction are taken and then counting them. So if I outputted this count global at the end, I would see all of the different paths and all of the different functions of the BRIF instructions and how many times the true or false branch were taken for each of those. So here is a list of the different instrumental events that we want to have. We want to go down to the bytecode granularity and then up to granularity like thread, GC operations, function enter exit, memory and table accesses, component operation events. So when I enter or exit or within the WASI components, we want to instrument those things as well. Begin and end events. So these are things that are provided by dtrace specifically, which are really nice. So when my Wasm module starts and when my Wasm module ends, I want to execute some logic, traps and exceptions. And if there are other events that would make sense for anyone else's use cases, you should reach out because that would be helpful for me for brainstorming these things. This is all theoretical with my limited scope, but y'all have a lot of experience, so it's helpful to pull from. So if you think about developer tooling at a high level with the possibility of whamm in that context as well, it could be pretty impactful, especially since so many languages can compile to Wasm. With whamm, you can write instrumentation once, and it can work in a lot of different contexts, either leveraging the engine capabilities as available or using bytecode rewriting to support all the different contexts that doesn't work for your engine. You could really hack the planet. Like in the classic hackers movie, we want to be able to hack everything, right? So with that being said, are there any questions for me?
Sure. So awesome work. This is really, really cool. Thanks. So I have a question. You have this trade-off even here on the slide between directly implementing this in the engine versus doing bytecode rewriting. And you mentioned flexibility, I guess, like you can dynamically turn this on and off if it's directly in the engine. I imagine you do like the optimization or something. Mm-hmm. I wonder if you've measured the overhead of like how low can you get it if you have the Wasm instrumentation approach, but you have like a global Boolean flag and maybe even recognize that specially in the engine?
Yeah, I'll have to check and see. One trade-off there as well is that like if you think about an engine supporting instrumentation specifically versus having bytecode rewriting. You could have any monitor that you just turn on dynamically versus you have to have every monitor that you may need at any time in production. And also you would need to be running the instrumented production code as well. So there are some trade-offs with that, but also that would be a good test to do to see the overhead of the de-optimization along with the overhead of the global check.
You support even like turning on dynamically up the stack like OSR to get stuff turned on. That's pretty cool. Right, thank you.
Yeah.
Any sampling with these tools?
That could be a good mode to do sampling, because then you could like use statistics to figure out whether or not to fire.
I imagine maybe the predicate would be.
Oh yeah, that would make sense in the predicate. That could be a good feature for me to add for sure.
You had a random input of some sort. Maybe that should be okay.
Yeah.
This is super cool. How easy do you think it would be to implement whamm in a new bytecode rewriting framework? I'm thinking of Binarian, the WebAssembly optimizer. It would be super cool if we could just pass in this whamm DSL to Binarian and say, hey, instrument the code as a pass, maybe in the middle of the optimization pipeline. Would that be difficult?
Possibly, because I've never worked with Binarian before. So I don't know enough about that to be able to answer well, but it could be interesting if that's a good use case.
I imagine it's largely similar to Walrus for the purposes of this, right? There's just like a IR in memory that you modify to insert instructions and stuff. But like things like parsing the whamm DSL and like figuring out what instructions need to be inserted, would that be able to be shared? Is that sort of
oh yeah, it's all open source. Also, the way that it makes decisions about the how to inject. So you have like the normal kind of compiler phases where you have parsing, verification, whatever. So one of the phases is generating a behavior tree. So it's almost like an AST of the behavior to make decisions about whether or not to inject and what instructions to inject if the predicate evaluates to true. Because what's kind of wonky is that some of the portions in the predicate is sometimes statically defined and sometimes dynamically defined. And so you have to make decisions statically sometimes about whether or not to insert the predicate. And so if we had an emitter to work in the Binarian context, I think it would probably work because you just have to make that specialized. Yeah.
Hi, I really like this. One question that I had while looking at your example was there are a bunch of variables that are in scope in the whamm specification, like TOS and so on. Are these just sort of hardwired built into the language, or what is in scope? And
I have a tool to help reason about what is in scope when you have like this probe specification. So top of stack would be just accessible everywhere. And with the tool, it's easier to see what's in scope as well. And then obviously this would be in scope because it's a global. And then there would also be some special variables that are in scope because of this being a BR if instruction. So there are different things that are built into the language itself to help you intuitively define your probe logic.
My thought was there might be a way of linking this up with the previous talk and have something in SpecTech where you can say, here are the things that are available when you instrument based on context and whatnot.
Yeah, that could be interesting for sure.
So I also pushed her to do a neat thing. You can just basically say the tool info and give one of those specifications, and it'll tell you everything about what's in scope.
Do you have any plans to add like source level information? Like say, I'm writing Rust or C++ or something, and I want to instrument all of the updates to some field of a struct type, like wherever it happens.
I hadn't thought about source level stuff, but it would be interesting to leverage like the debugging metadata in Wasm to add some source level events as well, for sure. Good idea.
So how does this actually communicate with the outside world? So if I have a map like this, and I want to see the contents of that map once it's done executing, does it like automatically dump to a file? Can I hook it up to some sort of imported function? What kind of capabilities does WAM have there?
So what's nice is that WAM is super generic. So you could do a lot of different things. And since at a base level, all you're doing, like, you can provide this. So inside this, you could have it do anything. So you could have it every time this probe happens, this logic fires, I want to append to a file, or I want to send this data to a database, or like really anything. And then with like flushing things out at the end, that's where that begin end event comes in that I mentioned. So here, when the application tears down or something, you could execute something that just flushes all of my states so that I can actually reason about it, maybe visualize it, which is something that one of our REU students is working on, is visualization of the different output that can happen with our monitors. So there's like all kinds of things you could do.
If you have a in WAM data type like that map for the counts for the different branches, I'm assuming that's all within WAM itself and not in the instrumentation. That does that like, is that easy to access? Is that just like corresponding to some WASM global or something like that?
Yeah, so what it's doing at a low level is really leveraging, so what I do, since this exists, I'm not going to support maps directly in my instrumentation. Instead, I'm going to build like some map library in Rust, compile it to Wasm, and then when I'm compiling this instruction, I'm going to emit instructions that call out to my Rust map library, basically.
Oh, I see. Okay, so map is not primitive to WAM.
Right.
Okay.
Yeah.
Never mind. Makes sense.
Yeah, you can get waved. He's one that's doing the visualizations, by the way.
Yeah, hi. I'm mostly asking about, I guess I can talk about it more later. The intrusive, non-intrusive approaches. Do we have certain monitors that are not possible, non-intrusive, or certain monitors that if we do it intrusively, it will mess up the code? Is that something that we like worry about drastically?
There may be certain things that you can do with engine intelligence that may not be supported with bytecode rewriting, or it may just be way more complicated. But I don't think there's anything you can really not do in either context, or you can do in one, but you can't in the other.